Our next speaker is Eva. How to get this last name? I don't know.
It's difficult. It's Greek.
From Saclay. She'll talk about the role of magnetic field on supershell.
Yes. Thank you. Can you hear me? Okay, good. And I was told this changes the slides. Oh, good. So I want to take a moment and thank the two honorees and all the observers here for constantly challenging us and inspiring us to create new theories and disproving our theories. This is a list of my collaborators here. I'm working at CEA with Patrick Hennebel and Philippe André. And today I'm going to present some work on the evolution and interaction of supershells and superbubbles. And this is work we've been doing with Joan Dawson, and some of it was my PhD work with Andy Burkert and Katharina Firlinger in Germany. So first, I'm going to start with my last slide as well. Since we were talking about fibers recently, I want to show you some mysterious fibers that appeared in our simulations, and these have nothing to do with what I'm going to be talking about later. So this simulation is a big volume, a 50 parsec volume of 1 kiloparsec scale galactic simulation with feedback and adaptive mesh refinement, which goes down in resolution to 0.01 parsec. And well, one day, Patrick Hennebel came to us and showed us these big filaments and striations inside his simulations, and we're supposed to explain where they come from. So these are magnetic field lines here, and as you see, the magnetic field lines pierce through a sheet, and this sheet is oscillating, and in my interpretation is dragging the magnetic field with it a little bit as these wiggles grow. So if you project it, you see a magnetic field component along the fibers. So this is just to complicate things. Then I was supposed to find a reproducer for this, and I found it without looking for it in the simulations I'm going to show you later of colliding supershells in a turbulent environment. And maybe you can see them over here appearing in this cut in density where I'm only showing the gas at about 50 to 100 grams per cubic centimeter. And then I was like, yes, this is the magnetic field, right? This is a magnetic instability, and we should start quantifying as a function of the magnetic field. And then I looked at hydro simulations of a collapsing cylinder. This is isothermal, by the way, no cooling. And then they appeared like little wiggles here. I don't know if they're the same, but they're also small fibers on a sheet. So this is in preparation, but very much in preparation because we have to interpret it first. So if you have any ideas, find me later. And now for something completely different, or almost completely different. These are some images of supershells, and this is something I started working on in my PhD, as I said before. So these, as previous speakers have said, are regions that we see in various tracers, mainly in H1, in our galaxy and in other galaxies, and they're often associated with feedback. Here I learned that they can come from different origins, which is a very interesting possibility as well. So these supershells are supposed to fragment dynamically and/or gravitationally and trigger the formation of molecular clouds or stars. And this is because they are often associated also in observations with enhanced molecular gas or star formation, as Joan presented yesterday, I think. Yes. So this can come from a variety of dynamical instabilities. The most well-known was the one proven by Eva Vishniac in 1983, that if you have a decelerating shell, a ripple on the shell will tend to grow because of the, well, for a hard equation of state, because of the different sources of pressure on the inside and outside. So the material will tend to focus on the tip of the ripple, and the tip of the ripple will tend to grow. This is one instability associated with shells. So there is another instability, this is gravitational instability, collect a collapse model for star formation that is very well known, especially associated to H2 regions. So magnetic fields in this context have so far been investigated in terms of their effect they have on the thickness of the shock, but not very much on their effect on the stability of the shock as they bend around it. So another aspect that interests me a lot is the interaction of supershells. So yes, supershells can become unstable or not on their own, but what happens when they interact? Do we have a colliding flow sort of situation where a warm gas can transition to cold gas? And this small plot here is showing you my own recreation of Fabian Heiles' work from the early 2000s, where you have two atomic flows coming from the side, a high Mach number collision at a perturbed interface, and then you have the nonlinear thin shell instability creating ripples or growing the ripples on here, and the material on the at the tips of these ripples becoming thermally unstable and forming what he called molecular cloud precursors. So the question was, can this happen when you have two supershells colliding? Can this happen when the flows have very limited thickness? So this was what I started investigating in my PhD. And I found out that when we simulated the supershells, they became unstable before they collided, and actually you didn't need the collision to make cold gas. So what we did there, and this is very similar to what I'm going to talk about later with 3D, we placed two feedback regions in a box. This is 250 parsecs apart. So you have small spheres, in this case circles, in which the feedback from 30 stars is simulated. And this is based on stellar population synthesis models. So you have the stellar winds and the supernova explosions as a time averaged feedback. So the shells become unstable due to the Vishniac instability and the thermal instability. You have all these cold clumps that are barely visible on their surface, and when they collide, they get squashed, they are very elongated. So here you see some close-ups of only a couple of parsecs scale, where you see also the velocity structure of these. Now in 3D, it looks quite similar. This is a 200 parsec box with a mean density of 500 per cc. And here we have introduced some turbulence. So on the right, I'm showing you the thermal state of the gas in these 2D histograms on log pressure and log density. So we start the gas off at this unstable equilibrium point of the warm medium, and as it gets compressed by the shells, it moves into the unstable regime and gradually falls back on the heating and cooling equilibrium line and moves to create the cold phase that we see at the tips of these ripples here on the surface of the shells. Now, after the shells collide, you see that a lot of the gas is there in the unstable regime. And actually, when we zoom in, we find that we destroy a lot of the cold clumps that we created on the surface of the shocks. So it's not necessary that the collision will help make new or denser gas. And this is something we started investigating with Joanne. She showed the other day this cloud squashed between two supershells. And we wanted to prove that this could be because of the collision, because it's so nicely placed between the shells. So we compared with these hydro simulations I just showed you, and we measured how much cold gas you have in the area between these two radii of the shell. And this is shown here. So as a function of angle around here, you see the amount of cold gas. And this is a hole in the middle, where you can see the two components of the cold gas coming from the shells, and they collide in the middle, and you have, at best, the addition of these two components. You do not form any additional cold gas. So this could go in the direction of this theory where you need multiple compressions in order to form a molecular cloud. And we're starting to look into this, like driving this collision in a multi-phase medium. So what happens when you introduce a magnetic field? Here is an MHD case with a mean field of 5 microgauss initiated at a direction parallel to the collision axis. And this point has a residual flux along this direction, but also a turbulent component because we also derive turbulence before we make them collide. So in this case, you see that you still form a cold gas on the surface of the shells, but it starts to become very elongated, and this is because of the action of the magnetic field. It also affects the stability of the gas, like the thermal stability. You do not form as much as cold gas or as much cold gas as in the hydro case, because the magnetic field provides an extra pressure that changes the equilibrium of the thermal equilibrium of the gas. And this is a corresponding case of 2 colliding shells with a magnetic field perpendicular to the collision axis. And in this case, you see that on the surface of the shells, you don't have any preferential formation of cold clumps or filaments, but you do affect the global stability of the medium by providing the extra pressure because of the shocks. So you do not form any significant amounts of dense gas either. Well, this is a test I made just to start understanding what is going on, because you have magnetic fields, you have turbulence. So this is one bubble expanding in a very weakly turbulent medium with a magnetic field along one axis. And here is a weak field case, and this is a strong field case. So here you form all these small clumplets on the surface and small filaments. And here the thickness of the shell is so big due to the extra magnetic field pressure that it doesn't become unstable. So just to show you how it behaves statistically or globally, this is the expansion law of the shells. So the analytic wind similarity solution goes as time to the 0.6, and this is this black dotted line, and this is our hydro simulations nicely falling on top of that. This is a case that I did as a test with a very weak magnetic field, a beta of 10. This is the magnetic field parallel, and this is a magnetic field perpendicular. And you see that expansion law is also very affected. This is the gas fractions as a function of time. And since I'm running out of time myself, I just let you with the message that this is the hydro. You form a lot of cold gas. MHD cases, whether parallel or perpendicular to the collision, you do not form as much cold gas. And of course, this cold gas does not carry as much momentum or kinetic energy as in the previous case. So I will leave you with my conclusions and stop here.
Any questions?
I missed, and I'm sorry if it was totally obvious, what your original field orientation was for the colliding bubbles?
So there were 2 cases. This is along X here, so along the collision axis of the bubbles.
Yep.
And this one is along Y. So the big filament is perpendicular also to the field.
And the second part of the question was, have you thought of doing some synthetic observations of these?
I have, and since I saw Carl's talk earlier today, I thought of also making some power spectra of the magnetic field along the surface of the shell, and some rotation measure estimates for this. I must do this, yes.
Good.
Thank you. Nice talk. Actually, I want to know what kind of variation did you see when you changed the magnetic field strength from 5 to different values? And also, one question, why 5 microgauss as a week? I mean, why 5?
It was just a plasma beta. I chose a plasma beta of 1, roughly. So I ended up with 5 initially. So it's an equipartition in the end with magnetic turbulence.
And what value you give to the strong one?
That's a strong one.
5?
The weak one is something like 1.5 microns.
Okay.
The variation I saw was that the stability was more similar to the hydro case. Sorry.
Because in some MHD simulations by Hannay and Mackay, in the MHD magnetized evolution of BRCs in the HT regions, they have taken the strengths of range from 20 to 40 to 80 microgauss. That's why I asked this question.
Well, in H2 regions, things are different, and the field gets much more compressed around the region. You have a molecular cloud, the material is very dense, so yes, of course, you have higher magnetic field strengths as well.
Thank you.
Sorry, I'm afraid that we need to carry on.